Oh, what the heck just happened? There we go. Alrighty, welcome back, everyone, quote everyone, and this should be 6.2. All right, so your reminders of due dates are up on the screen, and I'm not always going to do this. A lot of the due dates you've got to get used to just being in the swing of things where, all right, we go over a regular section, then my math lab homework's due in a week. I'll tell you what the next Excel is, and then it's due in a week. I tell you a quiz, it's due in a day. We tell you the discussion boards, it's due in, and when I say a day, I mean a class day. So, a Tuesday to a Thursday or a Thursday to a Tuesday. So I might just start doing these things as like, more blanket announcements in Canvas or something instead of eating up class time. But for now, while we're still beginning things, I like doing it this way. And then that should be 2.2 and 2.3. So we have my math lab homework 1.1 due tonight, Excel heart rate due tonight. I know I only have, I think, one person that's turned in the Excel heart rate so far. Quiz 2, which is that video quiz on chapter 1. That's due tonight, and I think I've only got 2 people that have turned that in. You've got 2 My Math Lab homeworks coming up on the 4th. Remember, you need to keep practicing with Excel over and over and over, even if you think you've got it down. Keep practicing with it, because the more you use it, the more comfortable you'll be with it. If all you're doing is just trying to do the homeworks, it's not going to be, you're not going to have a good time all semester. You're going to be struggling. You're going to be missing some things here and there. And remember, when you're doing these Excel homeworks, pay attention to the instructions. The instructions are very, very, very detailed in what you need to be doing. So if you try to make a chart, kind of like how I did when we were going over the chapter 0 stuff, but the homework says you were supposed to use a recommended chart, which it often will, it will most likely mark it wrong, even if your graph looks good. So that is a typical problem, that students don't pay attention to instructions, and then they lose points because of that. And they say, hey, Mr. Beckner, why does it say I got 0 out of 5 on this? And that's another case of, if you went into it and read the grade analysis, you might have some hints about that. And I say might there because as we've said before, the auto graded homework, it's really good sometimes at telling you what you've done wrong, and sometimes it leaves it a little more vague. And sometimes that's intentional. Sometimes it's not. Anyways, the next reading, we'll definitely finish 2.1 today. We might get into 2.2. So by next class, you should read 2.2 and 2.3. Those discussion boards for 529 were already due, so we can delete that. So the discussion boards from last class are due tonight by midnight. Remember, don't answer everything. I've now had 2 different instances of this, students kind of talking about whether they should be answering everything or not. I've said it now, I think 4 times. Do not answer everything. Just answer the next one, maybe 2 questions if you really want to, if there's a lot of opportunity. If it's a discussion board where I only give like 3 or 4 questions and that's it, don't answer more than 1, because like I said, we're trying to offer opportunities for people to get their group work points, the stuff that we'd be doing in class normally. And then our next 2 Excel homeworks and their due dates respectively, 1.3 on the car loan. This one's not too bad, especially if you go back to the video where I did, is it a car loan or a TV loan? Either way, it's a loan, but we did the TV problem in class together, and the only difference between that one and what you have on your Excel homework is an extra column for a payment. And that doesn't really complicate things. You just have an extra column for payments. So you'll type something in the payment box, and then you might have to type something 1 row down, and then you can drag it down to fill all the rest automatically. The BMI is where things get more complicated, where I said you should probably you should definitely make a multiplication table on your own time in Excel using the formulas, using fixed cell references, because that's going to be amazing practice for the BMI, because the way you use fixed cells to make a multiplication or an addition table is literally the same way you'll use them in the BMI, but the BMI just has a more complicated formula. Instead of, this cell times that cell, it's got a fraction, it's got an exponent, it's got parentheses. So you have to make sure that you're practiced with a simpler one before you go to the more advanced one. Also remember that every single Excel homework has kind of a guided activity in your guided worksheets that we cover. We don't cover the Excel stuff in class. That's for you just to kind of look at and answer on your own if you feel like you need more help with this. All right, so that being said, this one. Chapter 2. So we have finished chapter 1. Chapter 1 was kind of an excuse just to talk about Excel a little bit more, honestly, because we throw in those fixed cell references in chapter 1. We kind of get into some slightly more complicated Excel assignments. But besides that, this section in terms of math is more about order of operations, very, very simple solving of equations. What am I missing? Order of operations, solving equations, and functions. We talked about what it meant to be a function. Inputs, outputs, inputs can't be, you can't repeat an input without having the same output. In other words, if you use the same input twice, the output should be predictable and it should be the same thing twice, or 3 or 4 or 5 times. And we said in terms of mathematical analysis, we don't really need to worry about what it means to be a function too much going forward. It's good to know. You should still understand that basic idea. But this is an advanced math class where we're going into the detailed analysis of what it means to be a function. It's more important just to grasp that if you put something in Excel, the output is predictable. You'll get the same output every time if you keep putting the same thing in, because Excel is always dealing with functions, the way it processes things. Okay, so chapter 2, chapter 3, and chapter 4 are going to be heavily focused. That's a lot of heavily, right? Very, very focused on something called ratios and proportions. This very, very simple idea that is seen all over our world, everywhere. And it's not everything, it's just everywhere. If you make a flat hourly salary, say $10 an hour, if you work 15 hours, or if you work 20 hours, or if you work 25 hours, your output, your pay, how much money you take home, is predictable in that these are proportional concepts. In other words, as one thing increases, another increases. And that's something that you're going to hear us talk about over and over and over and over and over. And with proportions, it doesn't have to be that. Let me get into the broader spectrum. When we get into the broader spectrum, it doesn't have to be as one thing increases, the other increases. It can be the other way. It can be as one thing increases, the other decreases. Now, it's not just a proportional relationship at that moment in time. It's something else. It's a little different. It's called inversely proportional. But the basic ideas are there that we can still run with. But we're going to hold on to the simpler stuff for now, that inversely proportional thing I just mentioned. I'm just saying it once and then we'll come back to it later. So let's go with the simpler idea for now. And before we even get to proportions, I'm building us up to what we're going to be going into ultimately. And then from there we get into percentages and percent change and all these things that we can relate to with, say, stock markets and our retirement plans and our savings accounts and coronavirus numbers and all sorts of pieces of information that we can analyze. So first brick in our house of proportional analysis, if you will, is the ratio. And the word ratio means fraction. The word ratio means fraction. In math, we have this fancier word called a rational expression. And when you hear the word rational, you think rational thought processes, you think philosophy. And in math, it has nothing to do with that. The root of the word RAT basically just means fraction. So we're going to have that root word be a rate, a ratio. You can go into crazier math and call it a rational, but they all just mean one thing. It means fraction. So what is a ratio? It's a way of comparing two sets of data that vary with each other, apples and oranges. You can also compare apples to apples or oranges to oranges. You can compare the same thing to itself, but when you get into that type of analysis, you have to be specific. You have to have a reason to want to do that. You know, maybe you're talking about different days of the week or something like that. So you're comparing apples on Monday to apples on Tuesday. I don't know, but you can compare the same type of data, but more often than not, we're comparing apples to oranges. So data that is proportional, that other word we've talked about, we'll see one increase as the other increases, and thus can be set up as a ratio. So anything that's proportional can be set up as a ratio. Anything that's a ratio can be set up as a proportion. It's a two-way street. Now, in the real world and in some of your homework questions or in some of these guided activities, what you may have to do is actually ask yourself, are these things proportional? If one of these numbers goes up, does that force the other to go up as well? And are they going up in the same type of relationship each time? Because there is a relationship as to how they should increase. And we'll get into a more specific saying with these ratios and proportions later, but for now, I want to leave it a little more open-ended. But the main idea for a proportion, for something to be proportional, the basic type, before we get into the advanced one, is if one thing goes up, the other should go up. So if your apples are supposed to be proportional to oranges in terms of sales, that means if your apple sales go up, your orange sales go up. And that just could be because of increased foot traffic. Does that mean in the real world that has to happen? No. Maybe you've got a store with a very limited inventory, or maybe your fruits come in all banged up one day, so your apple sales might go down. And because of that, your demand for oranges is going to be a lot higher because the people that were going to buy apples aren't going to buy these busted apples, so they go and buy the nice, pretty oranges. But again, you could have another store with just tons of inventory and it's all beautiful, and just on Monday there's really low foot traffic because everybody's tired from the weekend or something like that, just getting back to the grind. Or coronavirus is happening and no one's at the store. So on Monday, maybe you sell like 2 apples and 3 oranges, but then on Tuesday the foot traffic increases, people need their food, people are allowed back in public, whatever it might be, and now you sell 200 apples, so maybe you sell 300 oranges. Now that's a drastic increase, but no one said the increases have to be small or large or medium size. They can be whatever, as long as one increases and the other increases in a predictable manner. All right, so what are the two things that I say we're going to say in here over and over and over and over and over? Pay attention, and does it make sense? Pay attention, and does it make sense? Ask yourself, does it make sense? Anytime you do a problem, you should ask yourself if it makes sense. If you aren't asking yourself that after every single problem you do, then I have taught you nothing. Does it make sense? Look, I'm writing all over the typed up stuff, so it must be important. After literally every single problem you do, if you find yourself making mistakes, ask this after every single problem you do. Now, I clearly don't want to leave that up there, so let me erase it. I just like to be emphatic at times. We're having fun. So the other thing that I don't always say, but I do feel is as important, is to use your words. Use your words, use your words. So many people want to be lazy and not set up a problem. They just want to go straight to the numbers, straight to the solving process. And in a quantitative reasoning course where every other problem we do is a word problem, if you don't set these up, if you just want to go straight to the brass tacks, even me, even your teacher who's pretty good at math, I'm pretty okay at math, if I don't use my words, guess what? Every now and then, make mistakes. Especially with these ratios and proportions, when we're going to have more than one of these things, it's really important to use your words to set up a fraction. Remember, ratios are fractions. Ratios are fractions. So this apple slash orange, the way you would really write that is apple on top of orange. And your words don't have to be exactly what, it's just whatever you can relate to. So you could say the first thing on top of the second thing. It doesn't have to be first over second. You could go second over first. So if you're talking about a store selling apples and oranges on Monday and Tuesday, maybe you decide to go apples over oranges, or maybe you decide to go Monday over Tuesday. That would be fine. There's many, many ways you can set this up. There are 8 or arguably 16 ways. I won't say whether it's 8 or 16 because different math teachers can argue it's 8. Different math teachers can argue it's 16 because of symmetry. But the point of this is there are a lot of ways to set up a proportion correctly and get the right answer. There are a ton of ways to set up a proportion correctly and get the right answer. Now, for every right way, there's also a wrong way. So when you get a word problem that's a proportion, and it says the store sells 2 apples on Monday and 3 apples on Tuesday. I'm sorry, let me start over. The store sells 2 apples on Monday and 3 oranges on Monday. Then on Tuesday, it sells 200 oranges. How many apples did it sell? Something like that. There are 8 or 16 ways to set that up right, and then there's 8 or 16 ways to set it up wrong. And I think that's fascinating. But how do you know whether it's right or wrong? If you're using your words, that's going to tell you whether it's right or wrong. Because if you go apples over oranges on one side, but then oranges over apples on the other side, it's wrong. If you go, Monday over Monday on the left side, so you go Monday's apples over Monday's oranges, but then you flip-flop it on the other side, it's going to be wrong. You just have to have consistency. Consistency is key. Now, when you set these up, how do you go about solving them? You're going to cross multiply. Cross multiplying, what that means is, again, I'm just taking that file, the chapter 2 notes to share that you have in your homework. I'm just kind of filling in some details here and there. Remember, take good notes. Just because I write it down doesn't mean it's in your brain forever. You might have to write it down too. You probably have to write it down. So if you have A over B equals C over D, this is what a proportion looks like every single time. A fraction equal to a fraction. Cross multiplying means you take the top left and you multiply it by the bottom right, and then you take the top right and multiply it by the bottom left. So what we're doing here, this is just saying this turns into the A times the D equals to the B times the C. So again, what I've done is I took the A times the D, so those two things multiplied, and then I took the B times the C, so those two things multiplied. That's what we call cross multiplying because we're crossing top to bottom, bottom to top. Now here's the problem with introducing cross multiplication in a traditional math class. You got a fraction equal to a fraction, and you go, oh, cross multiplying is fun. This is awesome. This is easy. It's not too complicated, and that's true. But then they want to start cross multiplying everything. They see a fraction times a fraction. Oh, let's cross multiply. They see a fraction minus a fraction. Let's cross multiply. They'll see a fraction plus a fraction equal to another fraction minus another fraction times another fraction, and somehow they find a way to cross multiply that. And in all those scenarios, cross multiplication is not what you're supposed to do. Adding and subtracting fractions means LCD. Multiplying means go straight across and reduce. That last thing I said is above our pay grade, so don't even worry about it. Not the last thing I said in terms of multiplying. The last thing where it was like a fraction plus a fraction equals a fraction minus a fraction times another fraction. That's above our pay grade. That's what I meant there. So if you don't know what cross multiplying is, you better learn it yesterday, because we're going to be cross multiplying and cross multiplying and cross multiplying, and then we're going to cross multiply, and then we're going to cross multiply some more. So again, a proportion is 2 ratios set equal to each other. Ratio means fraction, so proportion is 2 fractions set equal to each other. And we say that if data is proportional, that means if one thing goes up, the other goes up. It also means if one thing goes down, the other goes down. It works in reverse directions as well. Now, let's take a pause and let's get into this stuff in a little bit. Let's go ahead to our guided worksheets, which are here. Da, 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 da. So here's our chapter 2 guided worksheets. It starts on, I don't even remember, what's it, page 63, something like that. Yep, there it is, page 63. Chapter 2, ratios. And they give a nice little summary here. In chapter 1, we said that a function was a study between, was a relationship between two quantities. So a proportion is just a special type of function, one in which, again, as one goes up, the other goes up. And they give some examples based on number of births, and they say, is this a lot of births? So in 2017, the US had 3,853,000 and some change births. Is this a lot? Is this a lot of births? Well, it sounds like a lot just as a plain Jane number, but you have to compare it to some other things to kind of get a sense of scale. What could you compare it to? Maybe the population of the United States, maybe the birthing rate previously. All of these could be good examples of things to compare it to. Other countries' populations and birthing rates maybe as well. So, okay, the US had 3.8 million, and they say this is down 2% from 2016 and the lowest number in 30 years. Well, that's kind of crazy because it's 3.8 million. So they go, okay, well, here's Mexico. They got 2.3 million. So 3.8 versus 2.3, well, oh, okay, US has a lot of births, it sounds like, because the US has got 3.8 million and Mexico's got 2.3. That's another 1.5, roughly, million births. But when you start looking at their populations, the US in 2017 had a population of 324 million, whereas Mexico had almost 200 million less people. So 200 million less people, and yet the birthing rate was only 1.5 less. 1.5 million less. I need to be more specific than that. So when you start looking at those numbers, you might go, well, I don't know, maybe these are a little different. So then they start doing it as a rate. And the word ratio relates to the word rate, as we said earlier. Rates are something we're going to study extensively, which are an extension of ratios. And that's where we talk about the number of apples per oranges, or the number of births per 100 people or 1,000 people or anything like that, or even per person. So what they do is they find the ratio or the rate of births per 1,000 people. This is a pretty common scale for people analysis and data. They do it per 1,000. Per 100 is nice because it's kind of like a percent, as we'll get into. Per 1,000 just removes a series of 3 zeros and a comma from your numbers, because then you go from millions to billions to trillions. So when they look at the population versus the birthing rate, specifically the birthing rate over the, I'm sorry, no, I had that right the first time. The population and the birthing rate per 1,000 people, what they get is it's about 12 births per 1,000 people in the US, but about 18 for Mexico. So that says when you look at this birthing rate scaled to the population, Mexico is reproducing at a, I don't know that I want to say significantly faster rate, but definitely a faster rate. 12 versus 18. I mean, that's 50% faster than the US. I think that's significant, but maybe someone would disagree with me on that word choice, so that's why I'm just being careful with my word choice. Where did I get that 50% more from? We'll talk about that in chapter 4. So there's other bits of information to consider in all of this. You might, oh, well, why is it such a small number per 1,000 people? Well, men can't give birth. Only women of childbearing age can give birth. So there's when they do this statistically, they'll have a minimum cap, and it's something like 11 or 12 or 13. And then a maximum cap as well, which is somewhere in the mid 40s, I want to say, maybe even up to the late 40s. And that's not to say that someone can't give birth before or after those specific years. Biologically speaking, it's certainly possible. These are just the averages of of when that happens. Okay, so just that quick little discussion aside, let's actually get into our guided activity now. And this one is always a bit of a challenge. People kind of stumble with how to say things, what they want to say, and getting it right as well. So this one might actually make more sense that I'm going to be kind of taking the reins instead of letting everyone else do so. So back in those earlier notes, not those notes, these notes, we said that in the real world, you may need to ask yourself if something is proportional. Ask yourself if one thing goes up, does the other go up? And then we also said, when you're trying to write out your ratios, to use words, come up with a thing one and a thing two, apples and oranges. And for the problems we do in our class, it's typically pretty easy to figure out what's the apple and what's the orange. But in the real world, that might be a little more of a challenge. So that's what this activity is kind of emphasizing here. So what are two quantities being compared in the following ratios? Be careful not to confuse units with the actual quantity. Now, I am actually okay here if someone used the units instead of the quantity. I don't really see a problem with that. So they say the gas mileage of a Subaru Outback, 35 miles per gallon, is a ratio, but the quantities are not miles and gallons. They're actually distance and gas. Because miles is a type of distance, gallons is an amount of gas. So they're saying to be very careful not to use the units, but again, in the real world, no one's gonna care about that if you're just doing this on your own. So I would not care if someone said thing one was miles and thing two was gallons, and then someone else said thing one was distance and thing two was gas. And in fact, the phrase gas is kind of weak in my opinion. It should be fuel, because not all cars use gasoline. Some of them use diesel fuel, which if you put gas in a diesel motor vehicle, you're going to have a bad time. Don't do that. Hold on a second. I gotta continue that. Ooh, that one hurt. That's why the diesel pumps are a very, very, very emphatic green color at the pump, so that hopefully everyone pays attention and doesn't do that. Okay, so we got a bunch of different ratios, and then we're supposed to say what thing one and thing two are in this. So GPA is 2.74. So your GPA typically goes from 0 to 4, hopefully nothing below a 2. Definitely, hopefully nothing below a 1.5 or 6, whatever it is, before you get put on academic probation. But what is this a ratio of? GPA is 2.74. So there's two numbers that you divide, two numbers that you represent as a fraction, that would come up with this 2.74 or 3.2 or 4.0 or 3.97 or 1.3, whatever it might be. Well, those two things are known as, and it is scary how no one ever knows this in class. I am terrified by the things that our kind of introductory week programs are not telling students anymore, like the fact that you should be studying 6 hours a week for a 3-credit class in the fall and spring, or 9 hours a week for a summer. Remember, 9 hours a week is what I expect of you outside of this lecture, or you're not putting in enough effort if you're not passing. So what are these two things? They're called quality points. Annotate, please. Quality points and credits. So when you make an A, that counts as a 4. But if you have a 3-credit class, you get 12 quality points because you get that 4, but for each credit. So 4 times 3 is 12. Those are quality points. So if you get an A in a 3-credit class, that's a 4 times 3, because the A counts as a 4 and then times the 3 credits. If you get a B in a class, that counts as a 3, so 3 times 3 would give you 9 quality points. If you get a C, that counts as a 2. I'm so sorry. So 2 times 3 would be 6. So you'd only get 6 quality points for a C. For a D, you get a 1. 1 times 3 is 3. For an F, you get 0 points. So 0 times 3 is 0 quality points. So you add up all your quality points from all of the classes you've taken, and then you divide it by the number of credits you've taken. That's the ratio of how your GPA is calculated. Now at TCC, we only have A, B, C, D, and F. There's no plus or minuses, but when you go to schools like ODU, Thomas Nelson, I'm sorry, not Thomas Nelson, I meant to say CNU, wrong peninsula school, please forgive me there. They have plus and minus grades, and there's some community colleges out there that have plus and minus grades, I'm sure, but not at TCC. And I don't even know if that, I think that's the truth across the state, but I'm only a TCC teacher, so don't hold me to that. But I think like an A minus is, what's that, like a 3.7, and a B plus is a 3.3. So the minuses are usually 0.7s, the pluses are 0.3s. And that could be different in another school, but that's how it was at ODU where I went. All right, so back on track. Only one US adult in 5 could calculate interest. So when they say interest, they're talking about like credit card interest, or the interest you earn on a savings account, or things like that, things that we'll study extensively in here. So only 1 out of 5 can do this thing. This is a very, very, very common, what was that? I think a bird just ran into my window. I don't remember if that happened in y'all or my calc class last time, but either way, a lot of nature going on. Everything's crazy. So this is what we call a part to whole ratio. This is a very, very, very common type of ratio that we will use over and over and over, which is why I circled it and put 8 asterisks next to that. If you don't write that down, I don't know what you're doing. A part to whole ratio, where we're studying a population or a group of things in total in comparison to a part that can or cannot do something. So that's what's going on here. We're looking at a total of 5 adults, and for every 5 that there are, only one of them can do something. So this thing 1 would be the adults, the US adults, who can calculate interest. I can't fill all that out. So the US adults who can calculate interest. And then thing 2 would be the whole, which is all US adults. 13% of US adults are numerate. Numerate means to be good with numbers. Guess what? Same thing's happening here. We are comparing a part to whole. We're comparing the part of the US who can do something to all of them. So what a lot of students will mistakenly do here is they'll say, oh, okay, we're comparing those who can to can't. No, that's not what's happening. We are not comparing can to can't. We're comparing can to everyone. So again, this is the US adults who are, this ... is just US adults who are numerate. And we're comparing that to, again, all US adults. That ... just means all US adults again. Percent means out of 100. So what this says is 13 out of 100 are numerate. Only 13% of Americans, 13 out of 100 are good with numbers. And as a math teacher, that statistic terrifies me. Now, am I saying that this is a true statistic? No, it's just something we're staring at in a workbook. I don't know whether it's true or not. I'm not going to take the time to cross-reference every single piece of data for this course, but I do cross-reference data in the real world. All right, APR of 6%. So an APR, an annual percentage rate, involves the amount of interest that you pay and the balance. So your interest would be the product of your balance and the APR. If you algebraically rearrange those, it says the APR is a ratio of the interest in your balance. This is one I don't expect people to get. Interest, balance, and APR are all tied together. If you know the APR and the balance, you can find the interest. If you know the interest and the balance, you can find the APR. If you know the APR and the interest, you can get the balance. As long as you have two of those things, you can find the third. Speed is 75 miles per hour. Miles per hour. The word per means fraction. So something that comes after per goes in a bottom. Something that goes after per goes in a bottom. Something that comes after per goes in a bottom. If I say something 3 times, you should probably write it. If I say anything, you should probably write it, but that's, So that's miles over hours. Now up here it said don't use units, so I could write miles and hours, but I'm not gonna. I'll do what they asked me to. But again, if a student wrote miles for thing 1 and hours for thing 2, that's fine. But more appropriate name is distance and time. Miles is a type of distance, hours is a type of time. Because speed can be measured in many different types of units. It could be meters per second, it could be feet per hour. It could be kilometers per day. So saying a distance to a time is a much more general thing 1 and thing 2 to represent a speed. Half of 17-year-olds don't know enough math to work in an auto plant. Another scary statistic. There's a decent amount of math that you need to know to work in an auto plant, apparently. Probably because they work with computers. They end up, programming dimensions and things. There's a lot of different nuances, and I certainly have never worked in an auto plant, so I don't know too much of them, but I've seen just a little bit here and there. Again, the point of this is half of a total population don't know blah, 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 blah. So we're comparing, not the ones who can to can't, and in this situation, we're focusing on the don't aspect. So it's the 17-year-olds, not 17-yos, the 17-year-olds, I'm abbreviating, who don't know math, who don't know enough math. The 17-year-olds who don't know enough math. And then we're comparing it to all 17-year-olds. All right, the math SAT scores for elementary education majors compared to the national average is 483 versus 515. So we're comparing a specific chunk of SAT scores. What group are we specifically talking about? Elementary education majors. And what are we comparing to them to? The national average meaning everyone, basically, all students, basically. So we're comparing the SAT scores, the math SAT scores of the elementary majors to the math SAT scores of all students. You borrow $300 and pay $350 at the end of the month. $300 would be the principal, what we borrowed, and $350 is the new balance that includes the original principal and some interest. So this one is kind of a weak question because they don't say, is this the whole loan? It's a little sketchy, but what they're looking for here is principal and new balance. 52% of freshmen say their emotional health is above average. I would definitely say this statistic has dropped since this guided worksheet's come out for very obvious reasons. A lot's going on in the world right now. But anyways, not the point of the problem. 52% of freshmen. So when we talk about a chunk of a population, this is another part to whole ratio. So we're looking at the thing they're talking about in comparison to the total population. So it's the freshmen that are above average. AVG is my abbreviation for average, in comparison to all freshmen. You still have to be careful with the total because it's not everyone. I'm not saying all people because we're just talking about freshmen. 2 problems ago, we were just talking about students. The problem before that, we were just talking about 17-year-olds. So you have to be careful that when you talk about your quote, all or total population, that you're only talking about the total that you're, kind of partitioning. All right, 15.5% of students who started repaying student loans in 2012 were in default by 2016. This dry air is killing me. Okay, 15% of students who started repaying student loans in 2012 were in default by 2016. So default, that's not a good thing. It means you're struggling to pay your debt. You're not paying it in time. You can have lots of repercussions from that, especially with student debt. That's one of those debts that never goes away. If you file for bankruptcy, you can get car loans, you can get home loans taken away. You tend to lose your property at the same time. Student debt, thanks to the politics that have happened over the past couple decades, you're stuck with it. And that is a bad debt to be stuck with. Get rid of it as soon as you can. It's a great idea for you to be financially savvy in the long run, is to get rid of your student debt as soon as you can. But not the point of the problem. Again, we're looking at a part to whole. 15% of students who started paying ended up in default 4 years later. So let's just try and boil this down. It's the ratio of the ones who were in default I'm just going to abbreviate this and say after 4 years. So again, this says students in default after 4 years. So again, the 2012 to 2016, all that, et cetera, et cetera, et cetera, in comparison to all the students who were repaying their loans. We're not comparing this to people who don't have loans. We're just talking about the people who started paying their loan in 2012. All students were paying, again, starting in 2012. Starting in. It's a lot to have to cram into that small little space. Sorry for that. 50.3% of Americans projected to be minorities in 2044. And then Apple Incorporated reported 9.21 earnings per share. You know what? I don't want to. We're not going to do any guided worksheets on this. Let's just get these last two. So this next one is another part to whole. So this would be the minorities to all. And then whatever they're classifying as a minority here would also be classified as a minority here in comparison to all Americans. And then Apple reported 9.21 earnings per share. So the word per right here, we said several times earlier, is telling you in a fraction what comes after. So the earnings would be the top and the shares would be the bottom. Earnings, another word for earnings is profit. All right, so I'll leave that up for another like 20 seconds, but then I need to clear my screen so we can move on. Okay, let's clear. Let's go up, annotate, and scroll down. So, using ratio tables to set up proportions. This idea is going to get used over and over and over and over and over and over and over in here. What are ratio tables? How do we use them to set up proportions? So we're going to have here is a ratio table. So any of this W, this B, this blank here, All four of those things, the W, the B, this blank, and this blank, as this is set up, they can all be found as long as we know this data is proportional. Now, in the real world, we'd either have to be told that it's proportional or use logic and reasoning to determine that it was proportional. In the class, we'll say, hey, this stuff is proportional. But before we get into the activity, let's go back to our notes. And now when my Windows key doesn't want to work again, no, I said that. I have to use my Windows key. That's what I meant to say. And we still need to talk about the stuff before the proportional table. So we already said this. A proportion is two ratios set equal to each other, where you'll go apples over oranges on the left and apples over oranges on the right, or Monday over Monday on the left and Tuesday over Tuesday on the right, something like that. Sometimes we're going to be asked to scale something to 1. Sometimes we'll have to scale it to 1 by logic and reasoning. We'll have to know to do that. Sometimes we'll also be asked to scale something to 100. Sometimes we'll ask to be turning something into a percent, which means to scale it to 100. So this is not the end-all be-all. That second line that is, but let's say, when you want to scale something to 1, make the value requested 1 and solve the proportion. So they might say, all right, the store sold 200 apples and 300 oranges. Scale the apples to 1. So the store, it might say, the store sells 200 apples and 300 oranges. Scale the apples to 1. That tells us which one to scale to 1. Or they might say, scale the oranges to 1. And again, that tells you which one to make a 1, whether you're going to make a top or a bottom 1. So you'd have a fraction with the 200 and 300, and then you'd have another fraction with a 1. It's just a matter of whether you put it in the top or the bottom. The problem generally will dictate whether it should be in the top or bottom. How do you know? You pay attention. Occasionally, though, a problem will not specify which one to scale to 1. So one of the rules of thumb, notice I said one of, is to scale the second quantity to 1. This is not the end-all be-all. Sometimes you'll scale the first one to 1 even though they didn't say to do that. But this is generally what you'll do. If not, maybe it's the smaller, maybe it's the larger. We'll get into that idea as well. Oh, look, does it make sense? Pay attention. How many times am I going to throw that in the notes? A lot. So again, this right here is just an issue that will come up every now and then, is they'll just give us 2 of them and say, all right, well, scale it to 1 or scale it to 100 or scale it to 1,000. And there'll be a reason to do that. Scaling something to 1 gives us a really, really easy way to set something up in a different type of format that's easier to just quickly bang out. Scaling to 100 gives us something to relate to a percentage. Scaling to 1,000 is pretty common with population dynamics, and we'll do all of these things. Before we get into that, proportion tables. These 3 lines, and I'll demonstrate this with an example before we get into the guided activity, in fact, are extremely important. You can be presented with a massive table of information, and as long as everything in that table is proportional, whether you have dictated that with rhyme and reason or the problem tells you that up front, you can find blanks in that table as long as you can draw yourself a box, whether it's figuratively or imaginatively. Actually, I should say figuratively or literally. I just said the same thing twice, basically. Whether you actually draw this box or not. And if you draw this box, you're trying to draw a box so that inside of that table, 3 of the corners of your box have numbers and the 4th has a blank or a variable. That will always enable you to solve for the blank or the variable. So in using a table, you need 3 corners of numbers and 1 blank. These corners do not have to be sitting next to each other. There can be gaps between them. They just have to be on the corners of the box you draw. So in other words, you need all values in just 2 rows and 2 columns, but it doesn't matter where those rows or columns are. So let's bump this down. Okay, so M and T here mean Monday and Tuesday. So I got a table, and on Monday and Tuesday, we know, let's go with that 2 and 3. We sold 2 apples on Monday and 3 oranges on Tuesday. So, maybe we're not a big grocery store. Maybe we're just someone on the corner selling apples and oranges out of a bucket. And I am told that this data is proportional. Which means as one increases, the other increases in a predictable manner. And then I say, all right, on Tuesday, we sold 6 apples. How many oranges did we sell on Tuesday then? So I could leave that blank, or I could have it be written as a question mark. Either way, I could write this as an X for being the unknown. There's lots of different ways to leave that as, the questioned value. So when using a table, you need 3 corners of numbers and a blank. Again, a blank could be a variable. These corners do not have to be sitting next to each other, but you should be able to draw a box around all 4 where 3 corners have numbers and the other is a blank or a variable. In other words, all your data, not nada, data, needs to come from 2 rows and 2 columns. It just doesn't matter where they are. All right, so here's what I'm saying. You should be able to draw a box and have 3 of those corners of the box have numbers and 1 be a blank. This is me drawing the box. So this is the box I'm talking about. The 2, the 6, and the 3 and the X are in corners. So this 2 is in a corner. This 6 is in a corner. This 3 is in a corner. And 3 of the 4 corners, the X is in the 4th one, have numbers. So you can set up a proportion doing this. And again, a proportion is just a fraction over a fraction. Here are many of the different ways you could set up this proportion and get it correct. So you could go, and this is my favorite way. The first way I like to do this is my favorite. My favorite way. I just write this out as I see it. 2 over 3 equals 6 over X. The top left over the bottom left equals the top right over the bottom right. That is the most obvious way to draw up a proportion because it's staring you in the face. You don't have to transpose numbers and you can get the answer. So what I'm going to do is I'm going to take this and cross multiply it to find out the number of oranges. Now, some of you with a decent amount of number scale, you might say, oh, if the apples tripled, they went from 2 to 6, maybe the oranges are going to triple and it's going to go to 9. Some people might accidentally say, oh, well, the apples went up by 4, so the oranges go up by 4. That's not true. Proportional means that they go up in a predictable pattern, but not necessarily the same for each 2 things. So cross multiplying means we'll take the 2 times the X. So we take the 2 times the X. We set that equal to. So I took these 2 and multiply them. Now I'll take these 2 and multiply them, the 3 and the 6. So the 3 times the 6. Or I could write the 6 times the 3. On the left side, I could have written the X times the 2. As I said, there's a lot of different ways to do this. 2X on the left, you don't really need the dot, but the 3 times 6 is 18. We can definitely solve this by dividing both sides by 2. 2 times X, whatever you do to one side, do to the other. You're doing opposite operations. Remember, this is a skill you're supposed to have at this level. Practice if you don't. So the 2's cancel on the left, and 18 divided by 2 is 9. So what goes in this block? A 9, and I really suggest using your words. Numbers need labels, so it's 9 oranges. That's what would go in this block. So as long as we can draw a box where 3 of the 4 corners have numbers, the 4th one has to be unknown. But without this 6, if this 6 wasn't here, I'd only have 2 corners with numbers. I can't do a proportion with this. That's not enough information. Or maybe it was the 3 that was missing. Maybe I got the 2 and the 6. That's not enough to do a proportion because I only have 2 numbers out of that box I draw. Do you have to draw this box? No. With practice, you'll probably stop doing it. But what the box is helpful for is how I'm going to set this up in a bit. when I'm going to take this problem and I'm going to make it a giant table. Before we get into that, though, I said that these proportions can be set up 8, arguably 16 different ways. So let's do this another way. Alternate way number 1. And I'm not going to do all the alternates. That would take me forever. So instead of going 2 over 3 equals 6 over x, instead of going top left over bottom left, let's just go top left over top right. So let's go 2 over 6. So I chose to do this one over this one. So I just got to be consistent on the other side. So I'll go 3 over x. Since I went left over right on this side, I got to go left over right on this side. So 2 over 6 equals 3 over x. And if you cross multiply this, you'll get 2x equals 3 times 6, which is 18. When you divide both sides by 2, you'll get x equals 9, the same answer. Alternate way number 2. I could go, instead of top over bottom, I can go bottom over top. So I could go 3 over 2, but as long as I'm consistent. So since I did oranges over apples, I can go x over 6. Bottom over top, bottom over top. So cross multiply, you get 3 times 6 equals 2 times x, which is 18 equals 2x, which is x equals, sorry, the x is on the other side now, not that it technically matters. Should give us 9 equals x. That's 3 of the, again, 8, arguably 16 different ways that you could set up this proportion and get it right. All of these are consistent. All of these 3 ways, and I'm not going to do all of them, that's where I'm going to stop in the correct ways, all of those are consistent. Let me pull up my red marker back for a second and have it be wrong. So there's 8 ways to do this right. There's also 8 ways to do this wrong. What if I wasn't consistent? So again, you got to go top over bottom, or left over right, or bottom over top, bottom over top. What if I do 2 over 3 for the left side? So I'm going top over bottom. But then on the right side, I go bottom over top. I go x over 6. If you cross multiply this, you'll get 2 times 6 equals 3x, which is 12 equals 3x. Dividing both sides by 3 gives you 4 equals x. And this is wrong. It is definitely not 4 oranges. That would not make sense. Why would the apples go up by 4 and the oranges only go up by 1? That's not a proportional relationship, as we will learn more about. Again, right now, all I've led you to believe is that one goes up and the other goes up. And you could say, oh, well, 2 went to 6 and 3 went to 4, so they both went up. But as you will quickly learn, I hope, is the idea of proportionality means that they go up. If one goes up a lot, the other should also go up a lot. If one goes up a little, the other should go up a little. But it's based on their original size. So why would something that was smaller go up 4 and something that was bigger only go up 1? That wouldn't make sense. So in all 3 of these ways, I never used my words, and I did that intentionally because I know what my students do. You don't want to listen to me. You don't want to use your words, and I get that. But if I had used my words, I could really help guarantee that I set these up right. I wouldn't make this mistake because when you don't use your words, you end up over here and you get a mistake. And if you're not asking yourself after every single problem, does it make sense? You're going to type it, you're going to write it, you're going to put it in, and it's wrong. So my favorite way, going back over here, the 2 over the 3, that was apples over oranges. So what I would have done out of the gate is I would have written apples over oranges for this one. So the 2 was an apple, the 3 was an orange, the 6 was an apple, the x was the unknown oranges. For this second way, alternate way 1, 2 over 6, 3 over x, that was going a Monday value over a Tuesday value. So I could write Monday over Tuesday. I'm just abbreviating because of space. So the 2 apples on Monday to the 6 apples on Monday. The 3 oranges on Monday to the x apples on Tuesday. I may have said Monday for 6 over here. That was Tuesday. Monday, Tuesday, Monday, Tuesday. Alternate way number 2, the 3 over the 2 and then the x over the 6. That was going oranges over apples. Oranges over apples. Oranges over apples. So I can go apples over oranges or I can go oranges over apples. It doesn't matter how you set up your proportion. There are lots of ways, 8, arguably 16 ways. But for every right way, there's a wrong way. Don't go flipping coins. Pay attention, use your words, get answers, ask if they make sense. Okay, so the same 2, 3, 6, and X, I want to put this in a bigger table now with a whole bunch of other fruits and a whole bunch of other days. And I'm not necessarily going to have the 2, 3, and the 6 be on Monday and Tuesday, but they're going to be in there somewhere. Stop licking me, Rambo. My dog is a nuisance. All right. Let's keep pumping this down. Oh. I guess he got mad at me for not letting me not letting him lick me on my foot, so he just shook his water all over me. Okay, distractions are fun. So big table, big table. I hope y'all at least laugh at my situation. It's funny. So let's have different fruits. Let's have oranges. It's really weird looking at oranges written in red. Let's have bananas. Let's have kiwi. Kiwis, is that the plural? I don't know. Kiwi. Let's have watermelon. Let's have apples. Let's have limes. Let's have lemons. And what's another good fruit? Tangelos. Okay, so there's all our different fruits. And then we'll go Monday, Tuesday, Wednesday. R for Thursday. You're in college. You should know that R is Thursday. Friday, Saturday, Sunday. There we go. Good enough. So there's our table. 1, 2, 3, 4, 5, 6, 7, 8 different fruits, 7 different days. And let's just have somewhere in the problem say that all fruit sales are proportional. And let's say that on, and like I said, the specific fruits and the specific days to before, they're not going to be all the same. And I'm going to throw some extra numbers in there as well. I just got to make sure that I'm careful to set this up correctly. I wanted to have a 7 here. I wanted a 12 here. I wanted my 2 here. I wanted my 3 here. And my 6 here. Let's have an 11 here. Let's have 100 here. And a 1 here. Okay. So I'll give you a minute to write down that table. Those of you who are following along live, not a minute, but maybe 20 seconds, 30 seconds. Make sure you get the numbers in the right days and the right fruit. So that's 7 oranges on Monday, 1 orange on Thursday. We got 11 bananas sold on Sunday. We got 2 and 6 kiwis sold on Tuesday and Friday. We got 3 limes sold on Tuesday. We got 100 tangelos sold on a Wednesday, 12 lemons sold on a Saturday. That's a Saturday. There is only one value that can currently be found in this table. So our goal is to find the only value findable. And what we're going to do is use this idea from before. When using a table, you need 3 corners of numbers and a blank. These corners do not have to be sitting next to each other. You need completed 2 rows and 2 columns for your corners, basically. It just doesn't matter where those rows or columns are. So here, apples, oranges, everything was nice and tight and sitting next to each other. So it was very obvious that the box was this way. 2, 3, and 6 were the 3 corners that have numbers. Then this was the unknown. You need 3 corners and an unknown. So if I go to draw a box, let's say I want this to be my box. Oh, let me just do the top left 4 here. If you drew this as a box, this is a corner that's known, but you need 3 corners that are known. You don't have that. You only have 1 known corner, so you can't solve a proportion making that your box. And a lot of people will just get stuck on trying to have these all absolutely next to each other. So maybe I do this. But again, no, that's only 1 number. You need 3 numbers in your box, so that's not going to work. Okay, well, maybe it doesn't have to be the top left with the number. Maybe you do it this way. And again, that's only 1 number. Once again, the main point here is you don't have to draw your box just around 4 like this. You can draw your box like this. But guess what? This, and this, these are your corners, and there are no numbers at all. So that would not work to make a proportion. I'm not saying those were zeros, I'm saying they were blanks. So you might go, okay, well, now I'm starting to get an idea. Maybe I do this as my box. Because then I've got 2 numbers that are in the corner. So the 7 and the 1 are corners, so that's a number, that's a number. But guess what? We've got 2 blanks as corners, so again, can't use that as our proportion. It doesn't matter what's in the middle of these boxes that I'm drawing, as long as 3 of the corners have numbers. Okay, well, maybe you draw your box like this. This has got a decent amount of numbers. I got the 7, the 2, the 1, the 6. That could work, right? The 7, that's in a corner. That's good. The 6 is in a corner. That's good. But guess what? That's a blank. That's a blank. So no, you got 2, but you need 3. The 1 and the 2, if you try and say 7 over 2 equals 1 over 6 or something like that, or 7 over blank equals 1 over 6, that would not work. So I'd love if we were in class together and someone pointed out what numbers form the box. And again, I could draw this 5 or 6 more times. Maybe you try and do this whole thing, something like this. That's almost all of it, at least. But again, no. 7, that's good. The 12 is good. But there's a blank here and a blank here. You can only have 1. You can't have 2. So no, that would not do it. Let's finally do this right. Here's a hint. Look for a row of 2 numbers. Then look for a column of 2 numbers that uses that row. The oranges, 7 and 1. So okay, we got 2 numbers in a row. That might work. But there's no other numbers in the 7 column. There's no other numbers in the 1 column. So you can't use the 7 and the 1. Look at the kiwis. You got a 2 and a 6. So this is a possibility. Because if you made your box something like this, just starting the box, you got 2 numbers. Now, if one of these columns on the outside of your box has an extra number, then you can make a proportion and look at this. There's a 3. So we can draw a box like this, where we've got 1, 2, 3 numbers and 1 unknown, and bam, we can actually do a proportion using that information. Again, I don't need any of the numbers in these 2 rows. I don't need any of the numbers in these 2 columns. I just need the corners. I need 3 of the 4 corners. That's the whole idea behind a ratio table, a proportion table. So what we do is we take the 2 over the 3. We set it equal to the 6 over, that's an unknown. So any letter you like, X, N, L for limes. Cross multiply, you'd get 2x equals 3 times 6, which is 2x equals 18, which is x equals 9. And now we're talking 9 limes. So this store sold 2 kiwis on Tuesday, 6 kiwis on Friday, 3 limes on Tuesday, and using that information, we're able to deduce, since we were told these fruit sales were proportional, that the number of limes sold on Friday is 9. And that really is the only other thing we can find from that table. Now, I drew this table in an annoying way that there was only going to be one value, findable, achievable. Usually, proportion tables are meant to set off a chain effect. When you find one, then you can find another, then you can find another, then you can find another. So that's what we'll see in guided worksheets. That's what we'll see in homework. So let's get on to that. The number of births in 27, we already talked about all that stuff. Well, no, we didn't. Was that 3.8 million? Is this a lot of births? To make sense of the statistics, we can make comparisons to the US population and compute the birth rate per 1,000. Given the fertility rate of 60.2 births per 1,000, for the women of childbearing age, they go 15 to 44. I think I said a lower number than 15 earlier. But again, that was just off the top of my head. So we can work backwards and compute the number of childbearing women. So what this table is looking at is, instead of comparing this to an entire population, let's just look at this as a comparison of women, because maybe it would make more sense to compare it with women, since men traditionally can't give birth. I don't even know that I need to say traditionally there. So in this table, we have a column for births, this 3.8 million and some change, then an unknown, and then a 60.2. Then we have a column for population. So when we talk about the population of 324 million Americans, there are 3.8 million births in that year. This next value, 1,000, is us scaling the total population to 1,000 people. As I said, very often we're going to be scaling things to 1 or 100 or 1,000, depending on the context of the problem, depending on the reasoning. And with population dynamics, to get rid of a chunk of significant figures, we often scale to 1,000. So they say, all right, well, what would that birthing rate be if there were only 1,000 people in the population? For every 1,000 people in the population, how many births do we predict? The next column is saying, all right, well, let's just find the number of women based on this population. Then let's scale the women to 1,000 instead of the total population to get their birthing rate. So the birthing rate based on just women is 60.2. So for every 1,000 women, there are 60.2 births. So our goal is to find the B and the W here eventually, but for now, we want to do this with simpler numbers. So the first exercise is, all right, let's just go, all right, there's 4 births for 500 people in the population. How many would it be if there are 1,000 people? Or if there are 12 births, how many people would it be here? But they only ask for a couple of blanks. They only ask for these 2 blanks. Very often with these proportion tables, they don't want everything. They just want specific answers, which are these 2 here. So let's start with easier numbers to get a feel for the solution technique, then come back and solve for the unknown quantities. Compute the ratio of births to 1,000 people and the number of women in this population. So I need to put my annotate on. There we go. So again, I like to draw the little boxes. You don't have to, it's up to you, but I suggest doing it. Do it with pencil, that way you can erase. So compute the ratio of births to 1,000 people and the number of women in this population. So the first one is going to be the births per 1,000. The second one's the number of women in this population. So this second question actually goes down here, just FYI. So question 1, compute the ratio of births to 1,000 people. Well, this right here is a column for births, and we're comparing it to the 1,000 people. So this is what we're answering for number 1. We need that blank. So this data is proportional. So that means we just need 3 corners with numbers. So you might say, oh, we'll draw this as your box right here. It's a terrible looking box, sorry for that, but you got a number here and a number here, but 2 blanks. So no, you can't do that. Maybe you think to do this. Maybe you make this your box and you got a number on the corner, the 4, you got a number on the corner, the 500, you got a number on the corner, the 12. So yeah, actually you could make a proportion using this as your box, but the thing that you're going to be finding is this spot here, which is not what they asked for. They want the ratio of births to 1,000. This is births to 1,000. So that's not what we want to do. We can fill a blank using that, but it's not what we want to do. So we need to make sure that this blank is one of our 4 corners. If you do it here, you're going to have a blank in the bottom right. If you do it here, you won't. The 4 is a number, the 500 is a number, the 1,000 is a number, and there's our blank. Now I'm going to have to erase this because I need to draw another box. I guess I could do the other box in a different color. I take it back, I won't erase it. So we got the 4, the 500, the 1,000, there's our 3 numbers, and here's our unknown. And let's give this the letter X for now. So we'll call this X. So we can go 4 over X equals 500 over 1,000. That's my favorite way to do it using a ratio table. That way you're just going top left over bottom left equals top right over bottom right. But again, I could go 4 over 500 equals X over 1,000. I could go 500 over 4 equals 1,000 over X. I could go 1,000 over 500 equals X over 4. I could go X over 4 equals 1,000 over 500. Lots of ways to set this up. Lots of ways to set it up wrong, lots of ways to set it up right. Cross multiply, you'll get 4 times 1,000 equals 500 times X, which is 4,000 equals 500X. Divide both sides by 500. And 4,000 divided by 500, 4,000 divided by 500, which is 8. Now that 8 goes here, which is a number of births when the population scaled to 1,000. So that's 8 births per 1,000 people. So if there's 4 births for every 500 people, there's 8 births for every 1,000 people. Let's pay attention to how these numbers changed because it's going to be the important aspect as we go forward. 4 births when the population was 500, 8 births when the population was 1,000. The 4 versus the 8, it seems like it doubled. 4 went to 8. The 500 versus the 1,000, it seemed like it doubled. That is exactly what's happening here. So the idea of proportionality that we say is one increases, the other increases, we can get a stronger statement saying as one increases by doubling, the other increases by doubling. So as one doubles, the other doubles. Or you could say as one triples, the other triples, or quadruples, quadruples. But they're increasing with a multiplicative effect that's constant. So for number 2, I'll do this one in blue. So we'll do number 2 in blue. Compute the number of women in this population. So the number of women in the population, well, the original population was 500 people, so we're trying to find this spot. This is our new X. This is now what we need to find right here. Down here just says if there were 12 births, then there'd be 900 women. Maybe we need that, maybe we don't. Let's find out. Okay, so we got to use the women block. So if you try and do this as your box, again, ignore the red stuff now. This would be a blank, this would be a blank, this would be a blank, that would be a number. It's not 3 blanks and a number, it's 3 numbers and a blank. So that wouldn't work. Maybe you try and do this. You try and use the 500 and the 1,000. Not you got a number, but blank and a blank. So nope, that doesn't work. Maybe you try and go like this. Remember that women where this box is has to be one of the corners. Number, blank, blank. Nope, that doesn't work. But if you use the entire table, now don't make these boxes with the labels, the birth, population, and women. Those are labels, not data. Do not make these boxes around data. What can be confusing is if your labels are numbers, and you're gonna see that later. So when we do it this way, the 4 is a number, the 12 is a number, the 900 is a number. 3 of the 4 corners are numbers. So we have our unknown. So if we call this our x this time, we can go 4 over 12 equals x over 900. You can then cross multiply. I'm going to write CM for cross multiply. That's 4 times 900 equals 12 times x. 4 times 9 is 36. That's 3600 equals 12x. Divide both sides by 12. And 3600 divided by 12. Well, 36 divided by 12 is 3. So that's 300. That's the number of women based on the original population of 500. So when the population's 500, there's 300. Sorry, when the yeah, I said that right. When the population's 500, there are 300 women. This is made up information. This is nowhere near true. It is typical that the number of women is about 50% and the number of men is about 50%, but it's not exactly 50. It's like a 51-49 relationship. And there are many reasons for that. Women tend to live longer. They tend to live healthier and safer lifestyles. But we're not getting into all those details right now. Okay, so using this idea, the numbers in the table are in the exact same location as when the numbers were uglier. So I got to clear my screen to be able to go back to what we saw before, which is the next problem. But again, the main idea, you should be able to think about a box drawn, whether you draw it or not, and 3 of those 4 corners should have numbers. That's how you can build a proportion from the table. So question 3. Okay, we are now ready to return to the original ratio table, solve for W and B. So they want us to find the number of women in the population, if the population is 324 million, back in 2017. And they want us to find the birthing rate per 1,000 for population. So we have the birthing rate based on 1,000 women, but now we want the birthing rate based on just 1,000 people in general. Now, I'm going to leave this as your guided worksheet activity for your discussion board. So annotate. So this will be your next discussion board. B and W, so that's 2 opportunities. So one student can find B, one student can find W. So find B, W, 1 student each. Sorry, that's not that clear. Blue was not the best color for that. So the next discussion board, the one that'll be due on Thursday by midnight, it's only 2 questions here. And I'm not saying that's the only part we'll have on the discussion board, just starting it out. I need 1 student to find W, and I'll have 1 student find B. And I will say that B is somewhere in the ballpark between 5 and 20. That's all I'm going to say. It's between 5 and 20. I'd like 2 decimals of accuracy. So 5.97, 13.78, something like that. The number of women is somewhere in the ballpark between 50 and 70 million. And let's have this be a whole number. Now, you're supposed to be asking if these make sense. The birthing rate between 5 and 20, would that make sense? Well, if it's 60 per 1,000 women. If you start including men in the population, well, that should obviously at least be half of that, so it should be 30, but there's something more specific about the women. It's not all women, it's only women between 15 and 44, and there's a lot of women less than 15 years old, and there's a lot of women that are older than 44. So those 1,000 women do not make up half the population. They make up, maybe a quarter of the population, maybe a third of the population, because it's not including all women. That's why the birthing rate is going to be less than 30. If you, for some reason, come up with a birthing rate that's more than 60, that wouldn't make sense. Why would there be more births when you start including men in the birthing population? That would make it less. The women population being from 50 million to 70 million, again, you might at first think that doesn't make sense. It should be about 160 million, but again, we're only talking about the number of women in the birthing age group. On average, again, yes, there are women who give birth before 15. There are women who give birth after 44. This is on average. It's not speaking absolutes. Okay, so that's your first two opportunities. So the first two students that come in can rock those. I need to clear my screen. So we can scroll down. And is this on both pages? I'm not going to go to annotate yet. Now let's complete the table from the chapter. So in your textbook, they've got, and like I said, you're supposed to be reading your textbook. I don't show it in class very often. I only do it when it's absolutely necessary because we have so much to talk about, but you are supposed to be reading your textbook. The textbook will very, very, very often, almost always, talk about problems that are in the guided worksheets or maybe stuff from the Excel homework even. It's all connected. So this table dealing with tuition prices for private four-year schools, public four-year schools, and public two-year schools. So this says, okay, the private four-year tuition back in 2013 and 14 was about 30 grand. So this is our Virginia Wesleyan tuition local to us. Similarly, the four-year in-state tuition, so not out-of-state, was about 9 grand. So that's our ODU tuition, which I'm fairly confident ODU costs more than that in 13, 14, but don't hold me to that. And then here's our TCC tuition at a mere 3 grand and some change. Looks very nice in comparison, especially to the private school. Some people say you pay what you get for. Some people say that those are diminishing returns. You don't know what diminishing returns are. Look into that for now, but we'll talk about it later. They say to determine the ratio of private four-year to public four-year with the second quantity scaled to 1 using the fundamental solution technique, which is the box thing I've told us about to compute the ratios. So what we're doing here is instead of showing the box and all that stuff, let's just do this the old school way. So they say, determine the ratio of private to public. Am I on annotate? No, I'm not. So we're going private to public four-year. So private, I got to zoom in a little. Clear screen, take off annotate, go back on annotate. There we go. So I'm going to go private to public, and I need to say four-year because there's public two-year as well. So this is me using my words and then writing extra things. So when I set up a fraction, I'm going to make sure I do the private school number on top of the public school number. So we're going to go one fraction equal to another fraction. And we're going private over public. And then they say to scale the second quantity to 1. So that's what we were kind of getting into before we talked about the ratio tables. We said just make the given quantity a 1. And they even kind of say in the table here, oh, we scaled this to 1. Scale the second quantity to 1. What's the second? Well, private would be the first quantity. Public four-year would be the second, which is why under the second, there's a 1 in this somewhere. Now, they didn't put it next to the 100 because that's another part of the problem. You can't have 100 here and 1 here automatically. The 100 here is scaling the private four-year to 100. That's not part of this problem. It's part of a later problem. Okay, so now you just got to be consistent. Private to public, private to public, private to public. Well, we have a private number here. We have a public number here. We have both of them. So let's make that the first fraction. That's the 30,094 over the 32. That's not right, is it? I didn't say public 2-year. We said public 4-year, public 4-year. So I need to undo that. Public 4-year, which is the 8893. I've got a later problem in my head. This right here, when I was talking about scaling to 1, that's not the one I'm referring to, actually. I pointed at the wrong thing. This is the one that we are referring to because we're scaling the public 4-year to 1. So we put a 1 in the public 4-year column and blanks in the other spots of those rows to find them, essentially. So we're scaling the second quantity, the public 4-year to 1. So that's why we put a 1 here. If they said to scale the first quantity to 1, then the 1 would go in the top. Because they said to scale the second to 1, the 1 goes in the bottom because the public 4-year is the bottom. Now, if you wrote public 4-year over private, that would change your game. Then the 1 would go in the top. But you don't put the 1 under the 30,000 because the 30,000 related to the 8,800. Now that means our x goes here. Then you can cross multiply and solve. Now, this is awesome. This right here is awesome, awesome, awesome. They say to cross multiply and solve, and that's what I'm going to do. And then I'm going to do it again in the awesome way. Cross multiplying gives us the 30,094 times the 1 equals the 8,893 times the x, which is just 30,094 equals 8,993x. Then we divide both sides by the 8,993. Which tells us if you do that division, what do you get? 3.4. Rounded to 1 decimal place, 3.4 is x. Now, in the table, what I've done here, if I had done the drawing of the box, this is the box we would have drawn. And this would have been our x. Now you might say, well, Mr. Beckner, you didn't write the 30,000 over x equals 8893 over 1. You wrote it this way. That's because there's 8, arguably 16 ways to set up a proportion. I just, instead of going top over bottom, I went left over right with this idea. And that was because of my word choice. Pause, hold on. Okay. So I mentioned that scaling the second quantity to 1 is awesome. Scaling the second quantity to 1 is awesome, and here's why. So in black, I'm going to show you the awesome way. We had 30,094 over 8893 equals x over 1. The right-hand side is just equal to x. Anything divided by 1 is itself. The left side, if you actually do the division, is 3.4. Instead of cross-multiplying, because the variable's denominator is a 1, you don't need to write that as a fraction anymore, so there's no need to cross-multiply. You can just do the division. It's so much quicker and easier. This is the reason we love to scale the second quantity to 1. Scaling the first quantity to 1 does not give us this awesome simplified version of a proportion, this awesome way that just simplifies like butter instead of having to cross multiply. Now, I'm all about multiple methods. I don't care how you get things done as long as you can get things done, which is exactly why I'm showing you all these different ways to do things. If you don't need to draw up the boxes, that's fine. If you do your proportions this way, whereas I always do them that way, that's fine. If you don't ever use this awesome way that I just introduced, if you always cross multiply and solve, that's fine. I'm just trying to give you a systematic approach to do things in multiple ways because sometimes one way is better than another way. because this awesome way doesn't work if the problem doesn't scale the second quantity to 1. We don't always scale the second quantity to 1. Sometimes we scale it to 100. Sometimes we scale it to 45.7. Sometimes there's no scaling and the numbers are just in place. So again, the strength of scaling a second quantity to 1 is that you don't have to cross multiply. All right, so now I need to clear my screen so that I can scroll down. For number 5, and this is the next discussion board. So I gave you 2 before. This is 1, 2, 3, 4, 5, 6 more. So this is our next discussion board. One student each answer the following. And I'm going to give these letters so that you can say the answer to A, the answer to B, the answer to C, etc. So this is A, B. Let me do it in color besides black. For emphasis, A, B, C, D, E, F. So we're doing A through F. One student each. Do not come in and answer them all. So I will punish a student at this point now that we've had this issue come up twice. So it's fine the first couple times. We have to learn from our mistakes. We have to get it right eventually. If you come in and answer all of them, I will not give you credit for it. Okay? There are a range of correct answers for this, depending on how you do it. So now what I would like you to do is all on your own paper, answer all 6 of them. That would be awesome of you. But when you go into the discussion board, just answer the next one. Do them in order. Do A. If a student's come in and has done A, then do B. If a student has done B, then come in and do C. Now, I understand that maybe there's 2 students working on the same thing at once. So if 2 students within a couple of minutes of each other post B at the same time, that's okay. But then the next student needs to come in and do C. So it is possible I'll give credit to 7 or 8 students for this problem. But again, it's only if it's a super, super, super close time constraint. If a student comes in and does A, and then an hour later another student comes in and does A, the second student's not getting credit. But if it's a student comes in and does A, and then 2 minutes later another student also posts A, then I'll give both of those students credit because the second student probably didn't see the first student finish. But you have multiple days to do this, and I know most people aren't doing this the second they finish class. So that's why I'm not too worried about that aspect. And again, there are a range of answers that can be accepted as correct for this. So I'm much more interested in the work. Show your work. Don't just say the answer is this. Say why. Type the proportion that you set up. Use, if you have a hard time, writing 30,094 over A equals blank over blank. I don't want to give too much away. If you have a hard time typing that part out, use your words. Use the words 30,000 over A. Then say after cross multiplying, you get 30,000 times this equals this times that. Then say after you solve, you get A equals this. So just imagine yourself drawing little boxes. If you need to get A, you need 3 corners with numbers, and then A would be the 4th corner. So maybe you try and do it like this. So maybe you drew this as your box. Well, the 100 and the 1 would be numbers and corners, but the C's blank and the A's blank. If you knew what C was, you could actually use this box to find A. Or if you knew A, you could use this box to find C. But there's a lot of different ways to find C. In fact, I will draw up a box for C without using other information. You can use borrowed information, or you can use just the numbers that were originally given. Every single one of the A through F is findable using just the 30,000, the 8,800, the 3,200, the 100, the 1, and the 1. You can find all of these only using the numbers given, but you can also find them once you have A, you could use that to find C. So C could be found with this box right here, number, 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 blank, or Once you have A, if you know A, you could draw this box to find C because you'd have number, 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 blank. But right now, without knowing A, I can't use this to find C. When you go to try and find F, some of you might just be really stuck on trying to use this and say, I can't find F until I find C and E, and that's not true, because you could do it like this maybe. If you use this as your box, you only need E to find F because you've got number, number. But maybe you want to do it without using any borrowed information. Well, maybe you did it like this. That box could get you F without borrowed information because number, 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 blank. So you should be able to find all of those. Now, the official answer to one of these might be, say, 100.5. Maybe a student comes up with 99.8. Maybe a student comes up with 100.7. Maybe a student comes up with 100.9. Ballpark answers for this are okay. It's okay to be a little off. And here is the reason for this. When you write the answer for A, spoilers, it's 3.4 because that's literally the problem we just did in the previous example. But nowhere does it say to round to 1 decimal. So maybe you round to 2 and you get I think it's 3.38. So if you use 3.38 here and then use that information to find maybe C or F or E, a student who wrote A is 3.4 and then finds C or F or E based on that is going to have a slightly different answer. And maybe a student uses A to get C and then C to get E, and these slightly different answers are going to have what's known as error truncation or error propagation. I said the wrong word, not truncation, error propagation. It means when you round an answer and then use that rounded answer to find another one, there's going to be an error. And then we use that rounded answer to find another one, there's going to be more error. And when you use that rounded answer to find another one, there's going to be more error. When you use rounded numbers to find another and then another and then another, the error tends to get worse and worse and worse over time. It's called error propagation. So if you wanted these to be exact, if you were going to use A to find C, you wouldn't want to round the answer to A. You might write it as 3.4, but you might actually want to use the 3.3892, whatever it is, when you're going to find C, which is why I'm suggesting to only use the 30,000, the 8,800, the 32, the 1, and the 100 to find those 6 to get the exactly correct numbers. So I don't want to tell what any of those are besides the 3.4. I'm going to suggest rounding to 2 decimals for all of these. But what's interesting is the teacher who filled out the answer key that we have in our book, they did 1 for some of them and 2 for others. So it's kind of ironic. I'm just glad it wasn't me that did that. Question 6. Now this stuff that I have right here, this did not go with question 6. I just wrote it there because it's where I had room. What number do you multiply by to go from the values in the second row to the third row, from the third column to the first column? I can't actually answer that yet without y'all filling out question 5. So I need to discuss later. But the main idea is that let's discuss this later officially, but for now, I'm going to put a fake number up here. So as a fake number in bright green, let's say that C was 100. I don't want to put a too specific number. Let's say this was 50. Let's say that the answer we got to C was 50. It's not 50. It is not 50. It's not 50. Let's just say this was 50. So what they're asking here is, what number do you multiply to go from the values in the second row to the third row? The second row to the third row. So this is the second row. This is the third row. So the A, the 1, and the B are row 2. The 100, the C, and the D are row 3. They want to know, what number do you multiply by to go from row 2 to row 3? This has everything to do with the 1. So the 1 in row 2 versus the value in row 3 dictates a multiplier. To go from row 2 to 3. It's all about the 1. It's all about the 1. To go from row 2 to row 3, you look for the element in row 2 that's a 1, if you have one, and then the number paired in the row or column, whatever you're interchanging between. So we're going from row 2 to row 3, you look for the number in the same column in the other row or the same row in the other column if they're telling you to go between columns. So because that's a 1 versus a 50, 50 is the multiplier. So for this, with me saying that C is a 50, which is not, 50 is the multiplier. So in other words, if you know the number here that is A, let's say that this was a 2, you'd multiply it by 50 to get the number below, which is 100. Now I made up the A to reflect that. Again, the C is not really 50. This multiplying effect does not work with the true numbers. But the 1 is what's helpful here. You find a 1, and then you find the element in the other row or column, wherever they're telling you to go to, and that's our multiplier. So that's another reason to have scaled a quantity to 1, because it gives us a multiplier, and that's an idea that we're going to go with in later sections with what we call a constant of proportionality. It's just a number we can multiply one thing by to get the next thing. So if you know the number of apples, you multiply it by 50 to get the number of oranges, something like that. So let's say for every 1 apple sold, there's 7 oranges sold. If there's 2 apples sold, I can just take 2 times 7, 14, because the apples went from 1 to oranges 7. So 7's our multiplier. It gives us a way to do things even quicker than having to set up a having to set up a proportion, cross multiply, and solve. So if I knew this number here, if this B was, say, I don't know, a 10, that means D would have to be 10 times 50, which is 500. Okay, the second part of this is that, all right, well, what would your multiplier be if you went from the third column to the first column? You can skip columns, you can skip rows. All you need is an element that's a 1 somewhere. So third column, looking at column 3, so this is the third column, obviously making this over here the first column. So what would our multiplier be to go from the third column to the first? So you find the element in the third column that's a 1, which is here. Then you find the respective element over in the first column, which is here, this E. So this E value would be our multiplier. So let's say that E was, let's say it was 7. I used that number earlier. That says if you knew D, you could prove that this is 100 by multiplying it by 7. Or you take this 3200 and you multiply it by 7 to get 30,000. And again, I made up the 7s. That's not true. But what you can do is once you have all of A through F answered in the group discussion, which will be up no later than 1:30. If I have time, I'll set it up before 11 o'clock. I will do my best to set it up before 11 o'clock. But I have to prep for my next class as well and set up our video on Canvas and YouTube. Lots of stuff to do. But anyways, that's how you can find your multipliers. All right. I'm trying to decide which part I want to do next because I'm about 10 minutes shorter on time than I expected. I was hoping it was about 10:10 by now, but we have to ramble about a lot of other things now. I think I want to go ahead and call it a day. I don't want to throw too much guided activities or group work at you because you've got Excel due, you've got homeworks due. But you do, like I said, it's 9 hours a week that you're supposed to be putting into this class outside of class, including the 4 hours we meet together, meaning 13 hours of math a week. So if you think I'm assigning a lot of stuff, I mean, it's a decent amount, I'm not going to lie. But you should be able to do it all in 13 hours a week. You might say, Mr. Beckner, I don't have 13 hours a week for this class. That's a question of maybe you shouldn't be in the class. Unfortunately, you have to ask these things ahead of time. And that's why I feel like our schools should be really emphasizing to our students how much of a workload this stuff can consist of. Not all classes require the full workload, but QR, we require your time. So we're going to go ahead and call it a day there. That will finish up 2.1. There is another guided activity I might have us do. I might just throw up there as kind of catch-up points for students who don't have things initially. And it's page 69 and 70. So I just want to show it for a second. Come on. There we go. So ratios seem so harmless when presented in math class. 2 fishes to 3 bunnies as 8 fishes to 12 bunnies. In the real world, we run into difficult tables of information like this one. So that's why I had earlier, here's the basic math class table. This small little dinky apples to oranges Monday to Tuesday, but in the real world, our tables are much more all-encompassing, lots of fruit, lots of days. It's all about finding where the completed information is, things like that. Now, this isn't a lot of missing information, but it's a lot of information all at once. So they say, what does the number 541 represent? I'm not even going to get into that. But we have the number of students based on whites, Asians, Latinos, blacks, that's ethnicity, and how many of them are taking art and art history, how many of them took classics, how many of them took comparative literature. So these are different types of humanities classes, history, music, a foreign language, specifically Spanish versus another. Then total, then they have a ratio to the whites here. It's more about question 2 and 3 that I might throw up as an additional group work activity. Compute the ratio of English to art classes for each column. Scale the ratio so the second quantity is 1. So you'd be doing some A over B equals C over 1. We're scaling the second quantity to 1. So if we go first over second, if that's the words we use, so English to art specifically, English to art. So the A would have to be an English number, the B would have to be an art number, the C would have to be an English number, the 1 would have to be an art number. So they say go English to art, scale the second to 1. That's why I chose the second, the bottom, to be a 1. Round to 2 decimal places. So the C is what the unknown quantity would be here. So English to art for the 4 columns. So English to art, English to art. So here's the English. I'll demonstrate for the whites. So there's the English number, 1567, over the art. Well, that's art and art history, which is the 541. So we'd go 1567 over 541 equals, and we don't know what it is when we scale to 1, so x over 1. So it would be 1567 over 541 equals x over 1. See, the 1547 and the 541 came from the table, English over art. We scaled the second quantity to 1 because they told us to do that. And then we don't know this. You aren't going to have a number in here because with proportions, it's all about 3 numbers and an unknown. Again, that's not the answer to number 1. I'm just putting it there because that's the space I had. Sorry for me yawning. I'm stretching. So we have finished 2.2, which means its homework is due in a week. I don't have that in the Word file earlier, but you know that when we finish a section, it's due in a week. All the other due dates have been seen, so I'm not going to pull that file up again. So next time we'll go over 2.2 and 2.3. Maybe we'll have time to get into 2.4. I don't know. I'm not sure. Probably just 2.2 and 2.3, but we'll see what happens. So make sure you adhere to all the due dates, the discussion boards, your Excel homeworks, your My Math Lab homeworks. Remember, you get 5 attempts on Excel homeworks, excuse me. You have infinitely many attempts on every My Math Lab homework. The goal is to get at least a 90 on each My Math Lab homework because I said I'd add 10 points later, but the goal is really to get 100. But as long as you get a 90, you know that's perfect. So we'll call it a day. Email me if you have any questions, and we'll see you on Thursday morning or Thursday whenever you watch the YouTube. Take it easy.